Welcome back to my reaction to the Oak Ridge Nuclear Power Station in Roblox. This is part 2. If you haven't seen part 1, I'll pin it in a comment down below.
Leader move. I want some red. Let's get that red up to like 52. Yeah, 52 will do. Or insert a bit more. Whoa, 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 whoa. We're getting high. Okay.
Still trying to stabilize at 2100.
Let's work this out.
Another thing for the perspective of conserving fuel, you don't go above it and then drift back down towards it. That's not exactly the most efficient use of reactor fuel. Then again, considering we're not synced to the grid yet and we're already north of 40% power, that's apparently not the goal in this particular plan.
Insert more of this. Should pull more out. Wait a minute. I'm all the way in.
Biohazard warning? I haven't heard that announcement at the plant that I worked at. That really doesn't sound good.
I am. Okay. Oh, no worries. I can leave that at bay. Heat is pretty high. What I would do, or what I tend to do, I will turn this on. And then turn... is that cool?
That's also a little different. Before you even do a reactor startup, you would have all of your reactor coolant pumps or reactor recirculation pumps in service at that point. It's a bit weird.
It is. We want to keep... Alright, so basically with this, we want to keep this below 1200. We want to keep it below 1200 because 1200...
Yeah, that's generally a good idea. 1200 degrees Fahrenheit. You don't want to have localized power peaking.
Can lead to fuel leaks, which will lead to irreparable damage, if I'm not mistaken.
All right, so a little bit of thing on design criteria. There's no magic temperature that guarantees a fuel leak. There's not a simplistic heat level or temperature that you're automatically going to have fuel leaks, fuel damage, meltdown thresholds. That's not a thing. Now, fuel damage is tied to temperature, cladding integrity, in addition to reactor coolant system. In real life, there's no clean marker where 1200 indicates you're going to have a fuel leak. Now, I could see that in a video game, for sure, but real life's a bit more complicated than that. Another example of design criteria. So in a pressurized water reactor, normal operating pressure is about 2200, 2250 psi. The power-operated relief valves open at a little over 2300. The safeties, the spring-loaded safety valves operate at 2500. And the reactor coolant system was hydro-tested up to 2750. We know it's capable of surviving, but there's not a magical number that says, okay, at 3,200 pounds, there's a guaranteed chance of reactor coolant system failure. There's various design limits. For instance, the operating limit would be where the power-operated relief valve lifts in the 2300s. The design limit would be when the safeties lift at 2500, and the safety limit would be where it was hydro-tested to at 2750. By the way, not every reactor has those exact parameters. I'm just using a pressurized water reactor as an example. But the point being, actual failure will happen sometime when you exceed the outermost guardrail. These are just boundaries to ensure that you get nowhere close to that.
So, yeah, 1200 is a chance at fuel leak, and then, or it makes fuel leaks high. It'll make it happen.
So these are going to be from core exit thermocouples. Keep in mind that the actual fuel pin, the fuel pin center line, is going to be significantly hotter. Like, one number that's thrown out there is 2200 degrees Fahrenheit. At that point, your core is likely already breaking itself. Not guaranteed meltdown, but that combined with a few other things really increases the chance of core melting or fuel damage. But keep in mind that's the core exit thermocouple temperature. If that's reading 2200, then the fuel centerline temperature is probably well over 5,000. But you're extrapolating it because one, you're not putting a temperature probe in there. Two, most thermocouples don't go that high. And three, if you stick something like that in there, it's just going to completely ruin your reactivity model.
And once we get to above 2K, that's when a meltdown begins. So just make sure.
Okay, I know clearly what they're referencing. The 2200 temperature, it comes from emergency core cooling system acceptance criteria, as in, yeah, it's going to keep your temperature below 2200. And 2K, likely because it's a boiling water reactor. So I was licensed on a pressurized water reactor. Boiling water reactors, temperatures and pressures are going to be a little lower. So that does make sense. I have a sense of where they're getting that number from, but just to be clear, there's no magic number where a meltdown is guaranteed to occur.
To not get anywhere near that, but we should be fine now.
I don't know, one of them slashing buddy looks like you got a power paint.
As you can see, it's going down. We just need the one pump for the minute, I'd say.
1173 is a little on the spicy side of normal. Normal in a pressurized water reactor, core exit thermocouples are going to be about 700 degrees.
And we should be good.
And keep in mind, he's not even at full power. He's at like 40%.
I could moderate this, but I'm kind of lazy, so we're just going to work with that for the minute. And anyways, we should be fine nevertheless, though. We can moderate it after when the...
Just now running up the turbine to 1800 RPM while your reactor is already at 40. I know I'm harping on this, but to me, this is incredibly baffling of a design choice.
Reactor's running, but for right now, let's just try to get this on as quickly as we can. So generator turbine A, we want to... Alright, so this is what we want to do. We want to come back over here and we want to call the engineering department. So the number is...
It actually simulates you calling somebody. That's awesome. Is this an NPC or is this another Roblox player?
106 as it shows. Plug in 106. Just wait for the answer. Ring. Alright. Go to turning gear. Where we want to
inspection, expecting the turning gear, okay.
Disengage turbine A. Specifically turbine A. Now this is... Now here comes the tedious part, so... I'm not too sure exactly... Or I am sure, I'm exactly sure, but I've heard that this isn't as, you know... Isn't as readable as usual, but...
So what the turning gear does is it keeps the main turbine, which is basically a big old hunk of metal that consists of a lot of little blades, and that's where the steam goes in and parts on there, and that's where it spins it, and that spins a generator, and that makes electricity. The turning gear is to keep it moving, and it's really handy after you shut it down because it's a really big engine, so to speak, spinning around at relatively high speed. 1800 RPM for something of that size is reasonably fast, and it takes about 30 minutes or so for it to coast all the way down after a turbine trip shutdown and resulting shutdown. It's not exactly the best thing for a big piece of metal to slow down and then suddenly stop. A turning gear is to still give it a little bit of residual rotational motion to overall maintain its integrity and not have it warp too much. You also have spray systems, exhaust hood spray to quench it and ensure even heating as said big piece of metal coasts down, and it's all about long-term survivability of the asset. After all, this is the asset that makes money. But design criteria is not nearly as harsh for that sort of stuff since it has nothing to do with nuclear safety. The turbine's nuclear safety-related function is to trip offline and to divorce itself from the reactor so the reactor can shut down.
Pretty much you just want to mess with just mess with these and try to get the flow up to 0 right there. So, yeah. Okay. We want to get this number up to 1800 as it shows. And how do we do that? Oh, sorry. Okay.
And this, just like moving up the reactor, there's going to be designated hold points for engineers to take reading, but there's also going to be readings that you want to stay away from. And it depends on the design and shape of the turbine as far as what speeds to avoid, because those are the resonant speeds, as in speeds that it starts to vibrate a lot. And the turbine is big enough that vibration of 20 to 30 mils, that's thousandths of an inch as far as it's shaking, is enough to shake the entire turbine building and make it feel like you're having an earthquake. Needless to say, if the mils of the vibrations get too high, it's going to trip. So it is important to get out of those resonance regions while you are rolling up the turbine.
This is another thing as well. We want to make sure that this doesn't dip. Dipping is bad. This is something that we do not want, so we want to remove some rods. Which will...
Power sagging? Is that what he's talking about?
Bring our reactivity back up. Whoa.
Another reason why you should have the reactor offline is so you don't have to babysit it at some arbitrary holding pattern while you're rolling up the turbine. The turbine is already going to be rolled up long before you get to 40% power. After all, you sync it on the grid when you're at like 5-ish% power is what I'm used to.
Heat balance, yeah. Ignore it. Just continue to remove. And or insert.
Something printing?
And that should fix itself right there. Okay, yeah. So now we can come back to turbine generator A, which is what we just disengaged. We need to get this to 1800 and we then...
Alright, so it sounds like this thing has 2 turbine generators. That makes sense. I mean, this reactor is bigger than the one that I worked at if you're at 2100 and less than 50% power.
We need to make sure that this stays in the middle. And how we do that, we got to increase the flow and decrease the flow on the turbine and bypass valve. So
okay, flow balance.
Let's just bring
that
this
makes
up
sense.
to... I saw this in some videos. Just bring it up to 70.
Unauthorized personnel detected in...
Oh, you have unauthorized personnel. Usually that doesn't get announced on over the intercom. That's something that security is going to handle and deal with, but they have their own private radio channels for that. You don't need to blast that over the intercom and have people freaking out.
Sector A. All science, medical, and human resources personnel.
Being made just open.
Medical and human resources personnel. Some human resources personnel don't act at the plant I worked at, don't even have access to the protected area where the plant actually is. They just stay in the adjacent office building.
Evacuate immediately.
What is going on here? Oh, I like his little fun fact showing the energy density of uranium fuel pellets. More than 17,000 cubic feet of natural gas. It's probably even more than that, depending on the purity of your natural gas.
Big step to why we're doing this and how we get it to 1800. Not a big step, but just the main thing we're going to do. So we're going to bring this down to about, I'd say about here. It should start to...
Now the turbine roll-up speed isn't as exaggerated as, say, the reactor startup speed, but there are still going to be roll-up limits, though they're not nearly as harsh as reactor ramp rate limits.
Move, and then we bring it back to 35 once it gets down here. Yeah, so as you can see, it's flying up. Let's bring it to 35, which...
It is still pretty exaggerated, though, but I can see that for the purpose of a video game, no one's going to want to sit and wait 30 minutes for a turbine to roll up to 1800 RPM and stop at all of your little holding periods.
Could be. Should be. That one right there. There we go. We want to bring it down, try to get to the middle, and then to 35. That's what I like to do at least. So flow come down, and then this is where we use the precise knobs, which is just, it just makes precision. It's just, yeah, it's just slower.
Precision, just gonna tap it a bunch of times.
You can see now it's regulating
Fine versus course adjustment, I guess.
itself on 40 or 35, so we want to keep it on 35. And you just kind of mess with this until this gets to 1700. So yeah, just do that. And wait, I'll speed the...
Now, at the plant I worked at, this was actually closer to the magic control rod button in that you go to a set speed, you hit the go button, and it automatically goes there. That is... So the way the reactor works in this game is closer to how the turbine worked. And this whole bump and wait method, I've seen it for stuff like making an adjustment to the voltage regulator for the generator as opposed to the turbine, but you don't really see that a whole lot in a nuclear control room.
Wow.
Oh, he's getting it on up there.
Remember, security is the first step towards a safe work environment. Stay secure, stay vigilant.
You're not going to have like random security posts like PA address. PA addresses are really for an important plant announcements. Like he probably should have made a PA announcement when he was starting up the reactor. Commencing main turbine roll, for instance, is also a good reason because it tells people to clear off the main turbine deck, for instance.
Whoa, 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 whoa. Like I said, it will dip sometimes.
And this is why you have a primary reactor operator and a secondary reactor operator, so you don't have to do this nonsense. But I understand for the purpose of a video game.
So just, yeah, just keep an eye on it really, and you should be able to moderate it.
If you're at a holding period, you'd have your rod control system back in automatic at this point.
Okay, here we go. So now what you want to do, you want to turn on the synchronization. So what we're trying to do here, once we get to, let's say, about 86 to 90, or 1786 to 1790, just in that sort of area, you want to be able to click this button when this light lights up. It sounds... Okay, let me lay it out better. So
here's how it really works. The whole purpose of a synchronization is so you're in sync with the actual grid. And if anything, you're going to want to close your main generator output breaker, which I'm assuming that's the button he's referring to, when the synchronization is moving slow in the fast direction. Right now, it's moving fast in the slow direction, which means he's going to need to increase the speed of the turbine generator before you close the output breaker. Because after all, you're going to want it to pick up a little bit of the grid's load to ensure a smooth transition. Now, this is going to be a pretty big amount of energy that's going to be released. I don't know what would actually happen if you tried to sync the generator while you're at 40% reactor power, 2100 megawatts. Keep in mind, efficiency is going to be about a third, so as far as how many of those megawatts are actually on the turbine, it's going to figure out to about 700, but that's a lot. And you're going to want to even pick up a little bit of the grid to ensure that it's spinning the right direction, so to speak, and it is indeed acting as a generator and grabbing a little bit of the grid to ensure some stability. What you do not want is it to be going backwards, because that effectively is going to be turning your steam turbine into a giant steam pump, and that could cause a very damaging torque on your turbine generator system, more than enough to make it trip. You could even reverse power the generator, so it's gonna cause all kinds of unpleasant vibrations at this power level. It would probably cause pipes to jump about 10 feet into the air, and the main turbine is probably gonna trip on just about everything. Both mechanical and a whole bunch of electrical relays are gonna fire. So this is a pretty risky version of syncing the generator to the grid. I mean, that already in and of itself requires a high-risk briefing and additional oversight, just like starting up the reactor. So before he even thinks about closing the main generator output breaker, if this is anything like it is in real life, he's going to want to speed up the turbine.
when this thing here hits the red, this light's going to light up when it gets slower, because it'll get slower as it continues.
Okay, yes. The speed has got slower, and it's going to start spinning the other direction.
and then the light will start to bleed, and once we get to, like I said, 86 to 90, we want to be able to hit this button when it's on the red.
So in real life, you actually are going to want to press the button, really turn a switch. It's usually a pistol grip switch is how it works. And if this was a clock, it's going to need to be going clockwise, and you're going to want to close it when it's about 11:55, because it takes a little bit of time for it to react. So if anything, this red bit should be a little bit to the left of where it actually is. But I have seen operators mark this thing with devices just on sync scopes in general, whether it's the main generator, whether it's a diesel generator for testing the diesel backups. This is a critical evolution here.
And it should
just as much as starting up the reactor.
Calibrate itself to 1800. And then we can continue from this. So we just wait here a sec, about another 20%.
There it is, slowing down.
Now on reactor power. The beeping is starting to happen, as you can see.
These announcements are kind of silly.
You want to wait about 10 more percent. I like to do it 86, 87, just in that area. We wait a little longer. If you have a laggier PC or a laggier whatever, try to hit it around before.
It needs to be spinning the other way, though. Dude, no. So, slow in the slow direction, that is what you're doing when you are opening the output breaker. Taking something offline. Especially at this power level, if this was real life, he would have 100% tripped this thing on reverse power.
You know that, and if you have a good PC, then just try to hit it on the dot. Just as long as it's on the red, you're good.
I like that. Try to manipulate time to hit it, ideally. That's cool. It's a good video game tactic.
Okay, ignore that. That had no reason to do anything. What we need to do now...
You should get a few alarms when you take a generator online. You need to validate that it picked up some load from the grid. And then you would normally raise power to essentially compensate for that change. Now, I've actually never worked at a plant with two separate generators, but presumably you do it at two separate times, though you should probably have both turbines spinned up at 1800 RPM. You would just coordinate the breaker closures at different times. You wouldn't try to close them at the same time. But you would also be in contact with your dispatcher to ensure that they're ready for grid closure and that the grid's available to support this really big load that you're putting on to supply the grid. Especially if it's already at 2100 megawatts thermal, which is...
Reset you. We wanna decrease flow.
I saw the reverse power light kick in. Did he reverse power it?
Yeah, which should start making power. Very good.
Is that an achievement?
Very good.
All right, there you go.
Now
You got some generator megawatts.
Turbine flow up to the max. Like so.
Biohazard warning in sector.
Bada boom.
Should probably look into that biohazard. Shouldn't be related to anything he's doing, but I don't know what's going on there.
Easy as that. We're good now. Should stop making...
Okay, it looks like his reverse power alarm cleared. That is one important thing. You do need to get ready to increase load after you do that.
We'll come back to this later. There's something big here when it comes to making power for people. But that's when the thing is operating. That's probably the last thing I'll
Does it have you get with the dispatcher?
touch on.
Is that what he meant?
So now we need to do... Took those. And now we can start up the transformer here, which is... We need to turn on breaker 64 AM, which is this one right here, directly above 64B, which we turned on earlier. Flip that.
Okay, have this generator start supplying its loads. I mean, really, you'd have the aux loads already supplied from the opposite unit, or from the grid at this point, depending on the layout of the station.
If everything worked, that should happen.
Just turn the lights off. No, that's not normal to have it turn your lights off, man.
Like I said, if everything worked, one of these should be off. Now, what we need to call the engineer here. Again, 106, like it says. Wait a sec. Okay.
So it sounds more like he's calling the turbine watch the plant operator, because that's who would do the things with the turning gear while you're doing a startup.
We need to reset the breakers because we need that one on. Sometimes or most of every time, I'm pretty sure.
Yeah, you should probably do that before you actually sync the generator to the grid. Make sure all of your breakers are reset and all the flags have gone away, but okay. Yeah. If you had any trips, it wouldn't have let you close that output breaker.
When you do that, it trips one of the breakers and we just need them to reset one of them. And it should, we don't need to wait for it, but it should turn on. And they will call us when that happens.
I was talking about a different breaker. Okay, that's weird. If you had something trip, you need to investigate the cause, maybe get some electricians out there to take a look. But there's not really a situation where you would trip something during a startup and that would be normal.
We don't need to pick up equipment.
You normally trip things when you're shutting the plant down.
Like so. As you can see, it's on. So now, we need to get back to the deaerator. Relief needs to be 25 and inlet needs to be 45 on both this time. So these two here, we need 45 on this one and 25 on this, and then the same on this side. So, sorry. Yeah.
Okay, a lot of these things are a little backwards. Normally you'd have these feed water valves set to modulate, and these regulator valves would then modulate open as steam flow, feed flow increase while you're raising power in the secondary plant. All of these valves should already be armed at this point. Certainly at 40% power.
Let me bring this down to 25. And then the same with the second one, and we're good. 25, yep. And then
man, those deaerator temperatures and pressures are extremely low for 45% power. You'd usually see it at least 200 degrees and maybe 50 psi. It's like they're not even in service or something.
there we go. We can pick that one off, and now we want to turn on condensing pump 2 and feed it light. See, there we go again, condensing and fuel.
Okay, starting up and forward feeding additional condensate and feed water pump, that's probably the most realistic aspect of what you would do as you raise power. They're going to be at various thresholds, and 40% would correspond to about one of them, because a lot of systems say you have 2 strings of condensate and feed water pumps in series. They're probably 50% capacity each. The plant I worked at was a bit different. We had some that you had 3 40% capacities, but you'd also have a backup one just in case one of them trips, so you can maintain your feed flow and steam flow at 100% power. But yes, 40% power, not uncommon for starting additional pumps in the secondary plant.
We can turn on pump 2 now that we have sufficient power to it, if I'm not mistaken. That's why.
Though, if your power plant was this big, you'd probably have at least 3 strings. Better off having a bunch of standard size pumps rather than some specially designed ginormous pumps that I've never even heard of.
And we also want to turn on the bleed valve. This is the thing from earlier. And boom. Now, we can raise reactor power. Now what I want to do here...
So he's going to go all the way up to 3,000 megawatts before syncing the second generator. So you're going to want to have them kind of share the load, split the load. So if you're at 40% power, you're going to want to have both of your generators at 40% capacity, not just place one in service once reactor power gets up to the same level. You could conceivably do that, but again, it's just very clunky to try to sync something to the grid at higher power. You just don't do that.
This is something that I learned from another video as well. Turn it up to 3,000 as it needs. Before clicking that button... wait 1 sec, let me just... Now what we want to do, we want to turn A1 and A2 to speed free.
Don't forget
Again, the variable speed recirculation pumps. More plausible in a boiling water reactor, but still just weird to me.
B1 and B2 to speed 1, and A1 to A2 to speed 3, so... Let me check. A1, A2. So we want to turn this and this, and...
I like all the little fun facts. The one about the spent fuel in reactors just filling up a football field is 100% true. Though, the amount of containment structure you need to have them, they're going to be stacking pretty high. But the actual raw bits of fuel, if you just extracted that out and put it on the football field, it wouldn't take up a lot of space. It would be extremely hazardous, but it wouldn't take up a lot of space. But the dry canisters, you can bear hug those things, and you'd be 100% fine.
B1, B2, right? Nope. Oh, yeah. We'll turn B1, B2, A1. Okay. Got it. So... A1, A2, turn those all the way up, turn that one on, and that one on, and we run down here. We want to turn this one on and that one on.
You do need to watch your flow limits more carefully in a boiling water reactor. In a pressurized water reactor, you pretty much just leave it alone. But yeah, the point is you would need to have like a peer checker. You'd have a curve up to check out what your flow limits are just to make sure you stay within them. It's as critical as operating the rod control system.
If I'm not mistaken. And then we want to click that, start removing rods. There we go.
There it goes, just like
Hope
that.
you have no issues. I've had a lot of issues getting up to 3,000. I swear if I say this now and it starts going crazy, ignore the core heat imbalance.
Ignore the core heat imbalance. Very famous last words that sound like they were uttered in the Chernobyl control room.
We are fine. I don't know why I keep saying that, but, you know, just reminders. Yeah, I'm gonna speed up this part.
Another super fast ramp rate. Keep in mind that when you're above 50% power, you're required to go much slower. Going from 0 to 50%, not implausible to be there in a day, but from 50 to 100, that'll usually take a few days.
Okay. It should regulate itself. We can see there's a lot of heat in there. So what I like to do is turn that on there, and that should cool down. That's up to you though. That's not cooling down. Okay, we'll turn that one on as well.
Definitely riding the spicy side of these heat limits. 1500 degrees. You see, the 730, 800, that's closer to normal.
Well, there we go. Need to get to 3,000. Yeah. That should, in theory, cool down.
Yeah.
There we go. Slowly, but it's doing it. Okay, we'll just let that do its thing. We've raised reactor to 3,000. 1001. There we go. And now, we want to turn on the condenser coolant pumps B1 and B2 speed through. So, B1, B2, oh, well, would you look at that?
Don't recommend standing on the control boards.
Turn those on and that's exactly what we needed. And it should cool down. There we go. Cool.
So this is a bit of a weird design, but one thing that's important is to look ahead in your procedures so you know what's done next. Often there's notes and cautions that say, hey, these two steps should be performed concurrently or in rapid succession. So it does seem weird the way this is ordered. You should probably have your cooling pumps running and operational before you add additional heat.
So we'll just continue on. And now we need to move on to we need to move on to turbine generator number 2.
Just
Turbine
now
generator.
roll up the
So come
second
back
one.
here. We need to call the engineer.
Call the turbine watch again to kick it off the turning gear. It's crazy.
And now we want to disengage turbine B. Cool. Wait a minute, condenser cooling pump.
Vote kicking anyone who's misbehaving. If only you could do that to actual employees in the nuclear plant.
Ah, turned on the wrong one. Sorry. Okay.
Uh-oh. Plant status control event. You're definitely going to get written up and then pulled into a room and then asked if you want union representation. That's ugly.
Shit. We need to turn on B1, B2 here. And we need to turn these up to free. Yeah. Yeah, okay, that's right. Oh, I thought of something. I should still pull up. Okay. Well, yeah, there's nothing wrong with that.
Just the idea of toggling on and off reactor coolant pumps or reactor recirculation pumps when you're this high in power is just baffling to me.
Why that's on? That should in theory cool down. I'll leave it on now. Now we need to turn on generator B. Okay, so now I want to turn on this valve here so we can work with it. It's the same as the last one, but from what I feel, we're going to take it just a little slower. Just a little slower. Having some lag issues.
So that's what that was.
I don't know why this is happening, but yeah, just a little slower.
You're producing too much power, it's causing lag.
It's
Just now be rolling up the turbine.
Open that, ready. Keep an eye on power, of course. And just increase it ever so slightly. It will probably shoot up. Yep, there we go. Okay, as expected. It should. Okay, you're not coming down. If I shoot my thing up here, though, there we go. There we go.
Let's see. Will he do this one slow in the fast direction?
Don't forget, today is pizza day. So head on down to the cabin.
Today is pizza day. Man, if only. Most people who work in the control room bring their own lunch. I've never been a big fan of their cafeteria food, but your mileage may vary depending on where you work.
To grab yourself a hot slice.
Though people often do bring pizza into the control room for you, because they know that you can't leave the control room, because there's requirements about that. And if you're the only person there, and you gotta use the restroom, well, you're just gonna have to hold it.
Yeah, that's good. Reactor's good, I think.
These turbines are being very stable at less than 1 micrometer of vibration, considering how fast you're spinning these things up.
Yeah, reactor's okay. This one's
still
very
okay.
finicky, so just mess with it a lot. I'm just gonna speed this up here. It's pretty strict. Money!
Hey, you got a check. Oh, you didn't get anything that time.
It's pretty straightforward.
Oh, it's tallying. You didn't sell any electricity, though. I don't know what the markets were like in 1983. I wasn't even alive. There it goes. 1650.
Okay, and just like that, we've made it up to 1700. Turn that on. You know, the basics.
Just zooms in, glancing at the core from across the room.
Know the gist of it.
You're going to have a primary reactor operator monitoring the core at all times to see the effects on the core when you sync a generator to the grid.
Or you should do.
You're not going to see much, even though you're taking steam to spin it up. That's negligible compared to how many megawatts the core produces, but once it's actually rolling up and taking on more load, then yeah, that's when it becomes significant.
Basically the same as the last one here with the light and the button. 86 to 90.
Is he going to do it backwards again?
Regulated up to 1800. Of course, make sure that the flow is in the middle. Keep an eye on that. And of the reactor as well. Mine's pretty stable right now. I don't want to jinx it though, but you know, it's pretty stable for the minute.
One thing I will say is, as you get higher in power, you actually get more stable because every valve, every pump, every component is designed for sustained 100% power operations. So 100% power is actually one of the safest spots to be. He's not there yet, but he's reasonably high up in power. Above 50%, all your normal 100% power protective features are going to be enabled. Really, most of them at 10%, but the final one to go is permissives for emergency shutting down the reactor if something happens to the main turbine that causes it to
We'll see how it goes when we get to 1400, or get up to 4K, which is our goal. We get to 4K megawatts. Which is pretty straightforward, if I do it right. So, yeah.
Alright, he's going slow in the slow direction again.
The beeping's begun.
Really, it's set up backwards. This is what you do when you're opening the main generator output breaker.
With another 10 to go. Another 10. You got that at the right. Reactor power's holding itself. I think just one more round. Awesome. We made it.
They did
okay. Now
reverse power alarm.
So let's click that. And we decrease the flow all the way to the bottom. And up, we increase the flow on the turbine. So we increase turbine and then we decrease bypass. It will do that, that's just because the vibration's high. Ignore it.
Yeah, I can't imagine why your vibration would be high considering you almost reverse powered the thing at over 3,000 megawatts in your reactor core.
That should shoot right back down. Just acknowledge it. And you go and you move on. See how it's the same now? That should stay pretty much the same to each other for the minute. And it's meant to. We gotta keep those together as a similar. So now that we've done that, condensing pump 2, we get that up to speed 2.
Yep, starting additional pumps, that makes sense. Or increasing their speed. It's effectively the same thing. You're raising feed flow to match steam flow.
4,000 megawatts, so yeah. Put that in. Main circulation pump B1 and B2 at speed 3, which is okay, so B1 and B2, where is that? B2, oh, I've already done it. Well, I guess we can continue. Turn that on if you haven't already, and click this button to start moving rods. One of these. Get it up to 4K. Heat will rise, as you can see, it's gone up to 1200. We can fix that once things are out. We need to deselect this. Let's start working around the edge here. So, which ones have we pulled? We haven't.
Again, the arbitrary pressing of them rather than going by your detailed nuclear design report and what the reactor engineers have referenced after painstakingly done all the calculations for it. I get it for a video game, but it's just kind of funny to see that this high in power.
Those ones, so.
Motivational seminars are held in the faculty auditorium from hours 17 to 18 on Thursdays. Come on down and get motivated.
And I suppose we can do it on as well. Yeah. I don't know. Yeah, okay. We can do 2, 4, 6, 8, 10, 12. See,
This is
the
so
edges are
funny.
pretty... Ooh, okay. Yeah, so as you can see, the edges are pretty... And we're gonna turn that up.
Yeah, you're on the spicy side in the
That
center
should
again,
start
buddy.
going down. It's not. I'm gonna turn this one on here.
That is a very hot core, just overall.
While we're moderating.
It makes sense for it to get even hotter as you're going higher in reactor power. And after all, what 100% power is set by an agreement between the operator of the plant and the Nuclear Regulatory Commission. And your biggest constraint is going to be based on metallurgy, based on the cladding, based on the vessel, the reactor pressure vessel, based on your fuel assemblies, that sort of thing. Nothing's going to tell the neutrons to stop at 100% power. You can ask them, they're not going to listen. It's just a design criteria where you have guardrails around so you ensure it is not exceeded, so you don't overpower your core and risk breaking anything by being above its limits.
This, and then once it's over, we can start fixing it and start actually balancing it. But at the moment, we just want to keep water down.
And keep in mind, 100% power isn't the only thermal limit. There's going to be temperature limits on the core thermal limits map. There's going to be linear and axial and radial heat flux. That is to say, kilowatts per feet in the case of linear heat rate, per square feet in the case of axial heat flux, so per unit area. And those are all spread out in detail in your nuclear design report. But there's so much conservatism built in it. The fact that he's getting all these power peaking alarms, pretty unrealistic. It sounds like the reactor engineers did you dirty in terms of core design and gave you a ridiculously spicy core that never would have gotten approved. Because those calculations also have to be vetted by a third party as well.
I want to keep the power up, so you have our 12, start moving it. Because, as you can see, the edges are quite cold compared to the inner, and the inner we've been moving it.
That's weird. Having power peaking, because that's another thing. It's also can be expressed as a percentage, but having the center be twice as hot, that is ridiculous.
A lot. So, yeah. Let's start removing these eventually.
Yeah, I saw a 1400 number in the center and a 700 number on the perimeter.
Start inserting the middle ones. We just
keep in mind 700 is closer to normal just in general for the whole core.
wanna, like I said, we need to moderate it. Oh, it's pretty hot. Okay. I'll turn these up just over, and then we'll select a few middles.
I want to add another one of your additional magic reactor coolant recirculation pumps.
And we'll fix that. So, turn this all the way up. Okay. Now let's just deselect what we've got, and let's select our middle ones. Let's push those in more. Because we need to bring temperature down.
It's another reason why you do flux maps at...
Let's pull these out here. Let's bring it back down today, and then we'll just let water do its thing.
Now the whole thing's overheating. Huh.
Okay. Now, let's just turn on final circulation and let's pray that.
It seems weird to me that you don't have all your reactor coolant pumps running. Again, that seems like it would solve this. Maybe it's a way to make the game arbitrarily harder, like it doesn't let you. I don't know.
It goes down. It doesn't. Okay. Here goes. Just give me a moment while I try to fix it. If you're having the same issue, just select the ones in the area and bring them in. Okay. As you can see, it's working its way down.
There we
I
go.
realized that I hadn't turned...
It's all solved by starting these
I think
pumps.
either this one or that one on, so I turned that on and that fixed it. So now we're good. Now what we want to do...
Makes you wonder why you don't have them running all the time.
You are as well. Is that heat? Or heat and balance?
You got an alarm, dude.
Or no, it's not, sorry. That is pressure low. Okay. What I want to do here, just turn on the order control and acknowledge it. Simple as that. because I've been running at 4K too long. Usually you turn on by now, but I didn't. So now that we've done this and we've done that, we can move on to the last page. Now, here we go. We need to turn on the condenser coolant pumps, which are coolant pump A3, B3. We enable those. A3 and B3.
Oh, you should have had all these on a long time before reaching 80%, buddy. You usually have this set up before you start up the rest of the secondary plant, because it establishes a good solid vacuum in your condenser. Man, a lot of these stuffs are out of order.
And now we need to call the grid and get online. So we call it.
Call the grid and get online? You're already synced to the grid. What?
77. I think I did that right.
Hardest part, dialing you using an old school phone. Yes, I still had to use that in the real control room. You don't use your cell phones in the control room because it's a hardened structure. You don't get much of a signal.
772. Let's go. Okay.
Go online. What you'd normally do is you call them before you're syncing each generator. They don't have any control over what you do. You're just doing them a courtesy, and you're coordinating with the rest of the grid. This is a pretty big reactor, so you're going to have a noticeable effect on the rest of the grid. So it's mainly just to make sure all of their parameters are available to accommodate another really, really big generator.
As you see, we're officially online.
I don't know what that means for the purpose of this game. Maybe so you can start getting points for something. I don't know. But you're officially online the second the first generator output breaker is closed.
I'll show you how to, now our reactor setup, first thing we want to do before they give us orders, turn this one on, and turn, we want to turn that one on and that one on, and then just put in the code 150 for the minute.
Cheat codes?
Here on these ones right here.
Does this give your reactor extra lives?
So it doesn't get too high or too low and it doesn't conflict. We can reset that, it's all working fine. Alright, let's see here. So, I'm gonna ignore the reactor.
That's never a good thing. The grid's guys calling you back.
Alright, power demand's increasing. So, alright. Here's what it's asking us to do. It wants us, basically, we take 1190, and this is most of the job from now on. We want to divide this by 2. And once we get that number, which is 595, which is for me at least, we put 595 into the first.
Alright, so what he's talking about is operating a nuclear plant in a load follow configuration where the dispatcher tells you where to set power. That is not particularly realistic. It's not impossible to do, but you normally go up to 100% power and you supply base load. Other types of power plants respond to the dispatcher's requests for lowering power to accommodate changes in load or raising power, that sort of thing. I can understand that for a game mechanic, but you're not going to see that much in the real world. There are thoughts of bringing load follow back to nuclear and certain types of nuclear plants that are designed to handle some of that, but for the most part, it's just not the best use for nuclear power. Safe, reliable, stable base load power is what it excels at.
And then the second. These only go up to 750.
Okay, these are set points for the generators. Okay.
Megawatts if I'm not mistaken, but
750 megawatts each, so 1,500 on the grid total. That seems like you're leaving some on the table. Because if you're at 4,100 if you're at 4,100 megawatts-ish, you're a little over 80%. You should be able to get these generators up to, I mean, that implies full power is close to 5,000 megawatts thermal, which even a relatively inefficient secondary plant, you should still get well above 1,650. So your generators should be able to split up 825 apiece at 100% power. If you're doing less than that, you're just leaving stuff on the table, man.
So it's distributed between both of the turbines, and it will give us our ample power. Now, we also got to make sure the reactor is at the amount that is needed. I'm also going to turn this down a bit because we don't need all that.
Why? Oh, are you getting penalized for house loads having a bunch of pumps running or something?
No.
It's not significant.
Let's say, alright, we need to get up to 1190, so let's go to, let's say maybe 4,300. So what we want to do, let's take, as it says, main circulation pump C1, C2 at speed 2. So, circulation C1, C2, speed 2.
Make sure you go online, otherwise your power won't be sold. Heat
and balance. Okay. We want to and turn on the condensate feed water, so it's free on 1. So
yeah, you're still not at full capacity.
And come down to condenser. Turn it to free. Okay. And now we just turn this up to let's say 4,300. We set that, and we just mess with the control rods, and that's about the rest of the job.
Operating as load follow, so you would actually do something for the purpose of a video game. I can see that rather than just sitting at 100% for the purpose of a game.
I'll show you once I get there. I was having some issues, but I'm back, and we got a new order for a new amount. As it goes throughout the day, we'll ask for a new amount. As you can see, it's 1, so now it's at its highest.
One of the reasons why you don't want to adjust it is you don't want to have xenon spikes and valleys, which just make it annoying to have to deal with the xenon buildup and constantly having to adjust reactor power. You can manage it, but it's ultimately just not the most efficient for operating the entire grid to operate a nuclear plant as load follow.
1380. We divide that by 2. We get our number. Get that number, we put it into the reactor, which is 690 into the turbines. We put it into both. Turn that bad boy on, and then we need to make up all that power. So first of all, I need to bring this up to 4,300. So let's bring it up to about there. Now I'm going to start turning on cooling this.
This is all way faster than in real life too, but I guess that makes sense for the game.
Okay. So now we're at there. We want to be able to get up to 300, so I'd say maybe 4,500. Let's bring up to 4,500, so 4,500. Put that into there. We set that. We need to get C1, C2 at speed 2. Or, sorry, C1, C2 at speed 3. Everything's on here.
It's all security to deal with those guys.
Green pumps.
Evacuate immediately.
Condenser, cool pumps, A3, B3 to speed 3.
Weird for a low, middle, at high when you're all considered to be around normal power or high power. I guess for the purpose of the game, you have this little subdivision for the purpose of operating at low power. And that's an interesting take. It gives something to do, so it's probably an acceptable break from reality. Pretty
much will switch between those. That's probably why I was having the issue with heat. As you can see, it's all the way down here now. So that should be at speed 2 when it's below, but let's bring that to as its requested amount, so we can get to the number. I'll cut to when we can get that working. Alright. We've made it.
Reach 100% efficiency while meeting demand. I'm assuming that just means matching your demand. Obviously, you're not reaching 100% efficiency from thermodynamics perspective.
Just about. Oh, 100% efficiency too. I try not.
Probably closer to capacity factor, as in meeting your nameplate capacity if you're indeed operating at 100%.
To aim over, because it can go over, and I'm not sure what happens when it does go over, but I'd rather not go over.
Okay, I take that back. I don't know what it means for the purpose of this game. Relative efficiency, that's not a real term.
Over 100%.
I thought it meant capacity factor, which is the amount of time that you spent at your nameplate capacity. So you're at 100% power most times, and the only time you're not is when you're shut down during an outage, which happens once every 18 to 24 months. So your numbers are going to be well above 95, 98, 99% even, depending on how quickly you can do outages. That's the main thing. Otherwise, you're going to be sitting at 100% reactor power. But this relative efficiency, that's number doesn't mean anything.
To whatever is pretty good. So now, we've made it. We made it to the power grid. We're
Nice.
selling ample power.
Steaming and dreaming.
And now we can just relax. I decided to turn up to full 550. We should be running fine. Ooh. Like if you...
Also the megawatt numbers, because I just did a simple calculation, it's not consistent at what megawatt is 100% power, which is a bit weird.
If you see stuff like that, laser on, just come over here. Select the area. But it's starting to go crazy and just...
The manual Scram A35 is clearly a reference to Chernobyl, which I guess technically Chernobyl was a type of boiling water reactor, a very janky one at that. After all, the water still cooled it, but it didn't moderate it. It was the graphite that did that. But technically, water did boil, or was designed to boil, in the reactor vessel.
Insert some rods.
That's what it takes.
It should work itself out, as you see. And yeah, there we go. That's just pretty much my methods of working this. And you know, it's gone on for a few hours before I get bored.
You got the coffee.
Pop off, but it's pretty good. They're asking for a new order now, and yeah, it's pretty much the gist of working at the Oak Ridge nuclear power station.
An interesting take on a game. Is it realistic? It's more of a cartoonified version of reactor operations, which makes sense considering this is Roblox. I would say it's probably about as close to realistic as maybe Microsoft Flight Simulator was back in the day. But what I do really like about this is it gets people curious about how reactors really work, and it's enough that people are curious. It's not too realistic that it's going to scare people off. And that is absolutely a win, and huge props to everyone involved in the development of this mod. It has very high educational potential. I like the little factoids it spits out. I mean, it gets important systems names right for the most part, the casual relationships, the idea of managing flow balance in the secondary plant, of managing reactivity and power peaking in the primary plant. I mean, low technical realism, but in a way you kind of want that. Otherwise, it wouldn't be a very fun video game. Some of the steps being kind of backwards, but I think it really shows you just how, in a way, it shows you why things are so proceduralized at a nuclear plant. One potential thing as maybe even have like a crew of people, this should be a co-op type game. I don't know if it is or isn't, but have a primary and a secondary guy and a supervisor to just simulate what it's like to be a real reactor operations crew. It can even simulate various equipment failures in this game and see how they respond to them. Is it going to be as realistic as a simulator? Of course not, but it's going to get people at least a mindset of systems thinking, nuclear physics, integrated plant operations. I mean, it's still there. It's bare bones compared to the real thing, but it's still definitely there, and definitely enough to sate people's curiosity. I actually think this particular version is just enough realistic content without the actual realism to get people that are kind of curious about nuclear to get a little bit of satisfaction out of this game. So I do indeed appreciate. I appreciate anything that makes people more curious about how nuclear power plants work. Thanks again for the recommendation, and thanks so much for watching. I'll see you next time.